I have a question.
Yes.
So when they talk about quartile, it's talking about the deviation.
Okay, so quartiles, this was from 2.5. A decile, a decimeter, that's a tenth. A quarter is 25%.
Oh, okay.
So quartiles mean 25%. So the first quartile is 25%, or the 25th percentile. 2 quartiles is 50th percentile. 3 quartiles is 75th percentile, and 4 quartiles, that's 100%. So quartile just means 25%. I think that was, what was it, 20?
31 and,
Oh, 31, okay,
31 and 33. Yeah.
all right. The third quartile, 75%, yeah. Anything else in there? You kind of have to do the word problems in order for it to like click with you and make a little bit of sense. Using the inverse to find the areas. So inverse going pretty quick, right? Instead of looking at in the table. We're gonna start using the calculator a lot more for a lot of things that we do. Especially what we're gonna do right now. This is a population, a z-score. This is population standard deviation of population mean. This value right here is one value. So if you want to know, you take a state test and you're in 5th grade, where are you at compared to everyone? Okay, are you in the 70th percentile, the 90th percentile? Where is your score compared to everybody? Single score, one score. But what if we want to look at a group of people? We want to compare the group of people to the national average. Like our students. Like if I have 60 students, I'm an elementary school teacher, I have 62 students. I want to compare where our average is compared to the national average. Or a percent. Like, okay, Santa Maria High School, 87% of the students graduated from high school this year. What is that compared to the national average? Okay, take the entire sample. So we're going to take a sample and compare that to everybody. So we're going to use what's called a sample mean or sampling distributions. And instead of a z-score equals x minus mu divided by standard deviation, we just learned this, but we're going to elaborate on it. We're going to use a different z-score calculation. All right, so what does that tell us? That tells us that we're going to compare a sample mean. Remember, this is one value, x, your x value. We're going to take one value and compare it to everybody. Let's take sample mean, that's a sample mean, and compare it to everyone. So what we're going to do is use the central limit theorem. And that's the title of 5.4. So we're moving on to 5.4 in the book, sampling distributions and the central limit theorem. The way this works, in order to get these values, we got to figure out how to take a sample. So I'm going to look at the average GPA at Hancock College. Does anybody know what the average GPA is for all Hancock College students? Probably not. Okay. I don't know what it is. You don't know what it is. But in order to determine, we could take a sample. I could ask everybody here, what is your GPA? That probably will be representative of Hancock College, right? One sample. But in order to do this, we're going to take a population. And from that population, we're going to take a sample, X bar. And let's say the sample mean is 2.8. So I'm looking for GPA. What's the average GPA? Well, if I take one sample, if I ask everybody in this room and online, what's your GPA? And they tell me it's 3.1, 3.7, 2.6. I'm gonna get all kinds of sample values. I'm gonna get all kinds of GPAs. From that sample, I'm going to determine a sample mean. But is that representative of everyone in the college? We got like 10,000 students. So what I'm going to do is take another sample. So I'm going to call that X bar 1. I'm going to take another sample, X bar 2. I'm going to take another sample, X bar 3. So I take multiple samples, and then I'm going to average all of those samples. So if I average the means, I like to call it the mean of the means. Mean of the means. And the symbol is mu X bar. How is the average of a population determined anyways? How'd they get the average amount of apples consumed in a year? Well, we gotta take samples in order to make that decision. We can't just guess. I can't just guess what the GPA is for Hancock. So I'm gonna take a lot of samples and I'm gonna average all those samples. So the average of all the samples is going to be equal to the population mean most of the time. It's gonna be really, really close. So if I got 2.8, 2.7, 3.0, 3.2, 3.3, these are all sample means. If I average all those means, then I'm going to get close to the population mean. And the technical name for this is called the sampling distribution. Oh, there's that word again, distribution. That's just a lot of data. Distribution means lots of data. Sampling distribution for the sample mean. Or sampling distribution of the sample mean. That's another way, or of, either way. Another thing that happens, this is called the central limit theorem, and I could show you or take many samples, but and increase the sample size. What we're going to do is be able to target what the sample mean is going to be. And I usually do a bunch of labs. Starting now, I usually ask you to bring pennies to class and decide what the average year of a penny is, like the age of a penny. So we could take one sample, or we could take 10 samples, or we could take 100 samples, 100 pennies, and find the mean of those pennies and average all of them. That'll give me the year. Well, there's billions of pennies out there. All I need is a couple hundred of them to determine what the average year is. I take and find the sampling distribution for the sample mean, and that tells me what the population mean is going to be. Sampling distribution for the sample mean. So here's the sample mean, here's population mean. The mean of the means is equal to the population mean. The central limit theorem tells us that the mean is equal to the population mean. The central limit theorem also tells us the sample mean for the sample standard deviation, what I put here, is equals to standard deviation over square root of the sample size. So again, if I had 30 people and I asked their GPA and I get 2.6, then my sample size is 30. N is 30. So really, this comes from the central limit theorem. Central limit theorem says your population will be normally distributed, but also the samples. This is called the sample standard deviation for the sample means. So in the formula, we're going to calculate a z-score. I'm actually going to do this. If I'm given a sample size, like on the previous problem, the ground beef problem, if the population mean is 6 pounds, the standard deviation of 1.5. If I sample 20 people in this room, and I find that the average amount of beef consumed is 5 pounds, what's the probability of that happening? So I use z-score, calculate the probability of that happening. And now it's not a percentile, it's a probability, and that's why they use areas. Areas are probabilities, okay? Sample size is 20. Standard deviation is 1.5. Mean is 6. The sample mean, so I'm going to ask 20 people, sample mean was 5 pounds. We averaged 5 pounds of beef consumption for this class. Compare that to 6, 5 compared to 6. So we're taking this normal distribution curve and finding an exact value, okay? Finding a probability. That's defined on page, so you'll see that formula. Actually, this is on page 263. The central limit theorem is on page 263. The z-score formula is on page 266. This is right here is on page 266. If you're looking for it. So we need an example. We need to, in order to understand this, we kind of use an example. We need to say, okay, what in the world are you talking about? Well, we need a mean and standard deviation. Just like speed on the freeway. The average price of gasoline, let's do that. That's pretty important nowadays, right? So they usually when you watch the news, I don't watch the news anymore. I used to about 10 years ago, but I get my news. It's all on Twitter now. There's fire burning. It's on Twitter usually, or on Facebook or something. But on the news, they'll tell you the average price for a gallon of gas in the United States, and it's far less than California. I had someone tell me, well, gas prices are so high, I move into Texas, right? Because gas is so much cheaper. Oh, that's good reason to move. All your family lives there. Okay. If the average price for a gallon of gas nationwide is $4.50, with a standard deviation of 50 cents, I'm going to add and subtract from this. So I got a population mean of $4.50. I got a standard deviation of 50 cents. So I'm going to survey some gas stations in California, right? And see if gas prices in California are unusual. I'm going to calculate a z-score and get a percentile. This is a population distribution. So I'm on the news and I report the average price for gasoline right now. Do they go out and ask every gas station in the United States, how much are you selling your gas today? Or do they go to every state in the United States? Probably not. They're going to take some samples. So I can compare California, but I'm very sure that California gas prices are higher than the rest of the country. So if I think the average gas price is $4.50, I want to know what percentile prices are right now. Is it higher than $4.50 or lower? Okay. So surveyors, the news, CNN or whoever does it, right? A company, they call some gas stations. Let's call 30. Why is it always 30? I use 30 a lot. 30 is considered large enough. So usually your sample size is going to be about 30. Okay, 30 is big enough. It's not too small. Okay, so N is always about 30. So let's survey 30 gas stations. So if I go to 30 gas stations, and I find that the mean cost of gas in those 30 gas stations is $4.89. right now. Okay, I'm gonna do this. I'm gonna do this tomorrow, right? I call it 30 gas stations, and the average price for gas in those 30 gas stations nationwide is $4.89. How far away from $4.50 is that? Is that above average? Yeah, 489 is above. How far above is it? Well, that's the area to the left. So I'm going to calculate this as a z-score. But since we sampled 30 gas stations, we're saying, is this unusual for those 30 gas stations? So what I'm going to look at, this is called a population. This is called a population distribution. This is a population. I'm not going to look at the population distribution. I'm going to write this directly underneath here. A sampling distribution, the standard deviation. We're going to do this calculation here. So I'm going to find the standard deviation for the sampling distribution first of all. I'm going to take standard deviation, which was 0.50. So sampling standard deviation is 0.50 over the square root of 30. I got to do a calculation first. 0.5 divided by square root 30. 0.091. So the standard deviation for the sampling distribution is about 9 cents. For the population is 50 cents. That's all of the United States, right? That's everything. But a sample, based on a sample of 30, I get a standard deviation of 0.09. So I'm going to draw this directly underneath. And my distribution is much more narrow here. Wow, that's terrible. The mean of this sample is going to be about $4.50. So the mean is equal to the population mean. The population mean was $4.50. Okay. So I'm going to add 9 now. I'm going to put 4.5 there. I'm going to add 9. So not 9 cents, $4.59. I'm going to add 9. $4 and what is that? 68 cents. I'm going to add 9. $4.77. So is this 489 unusual? Where's 489 at? Not compared to this distribution. 489 is like right in here. 489 compared to the sampling distribution. What z-score is that? So I just wrote down the z-score formula. 489 is like way over here. I want to find the area to the left of that. So I'm going to do the z-score calculation. 4.89 minus 4.50 divided by 0.091. I just erased the z-score formula because I didn't have enough room. And do that math. .27. I got a z-score of 4.27. Then I'm going to go to my table and look up that value. In this table, we would say that this is off the charts. The highest z-score, 3.4, is not even on the table. 4.27 is not even on the table. That's 4 deviations. Like I said, 49 is way over there. More than 4 deviations away from the mean. I gotta do it on my calculator. How do I do that on my calculator? This is a normal distribution still. So I'm going to do normal CDF. And this is the only trick. We're pretty much doing all the same stuff that we did previously. How unusual is this? Well, actually, what I'm going to do is find this little area over here, the area to the right. Okay, that tells me I either find a left tail area if it's below the mean, or a right tail area if it's above the mean. So I'm going to use 4.89 as the lower bound. I'm going to use a really big number as the upper bound. The mean is 4.50. Standard deviation was 0.5. That'll give me 49 right about here. That'll give me that z-score, but I'm not going to use 0.5. I'm going to use 0.08 or 0.091. So that gave me, that'll calculate the z-score, and then it'll give me a percentile. It's gonna be a really small number.
So the lower bound is the mu.
Yeah. Yeah, so that was the average price for the gallon. That's like X. Previously, we used X. Now we're talking about the mean of X, the sample mean. So I'm just gonna drop those numbers in there. (9.1 E negative 6). 9.1 E negative 6. That's point. 5 zeros. That's not 5 zeros. 5 zeros and a 9. Okay. What are the chances of that happening? What are the chances? So it's kind of like a reverse proof in a way. I went out and I called and I asked, how much is your gas? And they said, oh, our gas prices are $5.10. Our gas prices are $3.80. We get the mean of all those numbers. $4.89. So we're disproving this number pretty much. So what's more likely? $4.50 or $4.89. Well, if I just called 30 gas stations, I got $4.89. That's probably closer to the true mean than this value. So I kind of disproved that $4.50 is the mean of gas right now, today, or tomorrow. That's what it was last week. Price going up. So this number is more accurate. We're kind of disproving that $4.50 is the mean. Because $4.89, your mean is going to be more likely the value that you need. GPA, if I'm looking at GPA of the college and I ask 30 people in this room, what's your GPA? Oh, the average GPA is 3.1. I think the GPA of the college is 2.9. So I compare 3.1 and 2.9 for a sample of 20 students. So the sample size is 20. I'm going to take a bunch of samples. Okay, I got 2.9. Where does 3.1 compare to 2.9? That's what the Z-score calculates. When we do this calculation, the Z-score calculates how far away these two numbers are. The distance. And if I want to find the distance between two values, I subtract them. And that's, again, what Z-score does for us. I like a couple problems here. I don't like example 4. I like example 5 because it's very similar to what we just did. Example 4 is about ages of drivers and how long it takes to drive to work. But example 5, again, I don't refer to examples very often. Example 5 on page 267. So here's the deal. I'm going to have you look at it, read it, try to digest it, and then I'm going to talk about it, and we're going to do it on our calculator. So do this right now, page 267. Example 5.